Chapter 8. Sound. Exercises pages 157 to 158. Exercises Q1. Page 157. Choose the correct alternatives. A sound carried by air from a sitar to a listener is a wave of the following type. 1. Longitudinal stationary. 2. Transverse progressive. 3. Transverse stationary. 4. Longitudinal progressive. Solution. Longitudinal progressive. Exercises Q1. Page 157. Choose the correct alternatives. When sound waves travel from air to water, which of these remains constant? 1. Velocity. 2. Frequency. 3. Wavelength. 4. All of above. Solution. Frequency. Exercises Q1. Page 157. Choose the correct alternatives. The Laplace's correction in the expression for velocity of sound given by Newton is needed because sound waves 1. Air longitudinal. 2. Propagate isothermally. 3. Propagate adiabatically. 4. Are of long wavelength. Solution. Propagate adiabatically. Exercises Q1. IV page 157. Choose the correct alternatives. Speed of sound is maximum in 1. Air. 2. Water. 3. Vacuum. 4. Solid. Solution. Speed of sound is maximum in solid. Exercises Q1. V page 157. Choose the correct alternatives. The walls of the hall built for music concerns should 1. Amplify sound. 2. Reflect sound. 3. Transmit sound. 4. Absorb sound. Solution. The walls of the hall built for music concerns should absorb sound. Exercises Q2. Page 157. Answer briefly. Wave motion is doubly periodic. Explain. Solution. 1. A wave particle repeats its motion after a definite interval of time at every location, making it periodic in time. 2. Similarly, at any given instant, the form of a wave repeats itself at equal distances, making it periodic in space. 3. Thus, wave motion is a doubly periodic phenomenon, i.e., periodic in time as well as periodic in space. Exercises Q2. Page 157. Answer briefly. What is Doppler effect? Solution. The apparent change in the frequency of sound heard by a listener, due to relative motion between the source of sound and the listener, is called Doppler effect in sound. Exercises Q2. Page 157. Answer briefly. Describe a transverse wave. Solution. Transverse wave. A wave in which particles of the medium vibrate in a direction perpendicular to the direction of propagation of the wave is called a transverse wave. Example. Ripples on the surface of water, light waves. Characteristics of transverse waves. 1. All the particles of medium in the path of wave vibrate in a direction perpendicular to the direction of propagation of wave with the same period and amplitude. 2. When a transverse wave passes through the medium is divided into alternate crests, i.e., regions of positive displacements, and troughs, i.e., regions of negative displacement, that are periodic in time. 3. A crest and an adjacent trough form one cycle of a transverse wave. The distance between any two successive crests or troughs is called wavelength, lambda, of the wave. 4. Crests and troughs advance in the medium and are responsible for the transfer of energy. 5. Transverse waves can travel only through solids and not through liquids and gases. Electromagnetic waves are transverse waves, but they do not require material medium for propagation. 6. When transverse waves advance through a medium, there is no change of pressure and density at any point of the medium, but the shape changes periodically. 7. A transverse wave can be polarized. 8. Medium conveying a transverse wave must possess elasticity of shape, i.e., modulus of rigidity. Exercises Q2. IV page 157. Answer briefly. Define a longitudinal wave. Solution. A wave in which particles of the medium vibrate in a direction parallel to the direction of propagation of the wave is called a longitudinal wave. Example. Sound waves. Exercises Q2. B page 157. Answer briefly. State Newton's formula for the velocity of sound. Solution. Exercises Q2. B page 157. Answer briefly. What is the effective pressure on the velocity of sound? Solution. Exercises Q2. B page 157. Answer briefly. What is the effective humidity of air on velocity of sound? Solution. Exercises Q2. B page 157. Answer briefly. What do you mean by an echo? Solution. An echo is the repetition of the original sound because of reflection from some rigid surface at a distance from the source of sound. Exercises Q2. X page 157. Answer briefly. State any two applications of acoustics. Solution. Application of acoustics in nature. 1. Bats apply the principle of acoustics to locate objects. They emit short ultrasonic pulses of frequency 30 kHz to 150 kHz. The resulting echoes give them information about the location of the obstacle. This helps the bats to fly in even in the total darkness of caves. 2. Dolphins navigate underwater with the help of an analogous system. They emit subsonic frequencies which can be about 100 Hz. They can sense an object about 1.4 meters or larger. Medical applications of acoustics. 1. High pressure and high amplitude shock waves are used to split kidney stones into smaller pieces without invasive surgery. A reflector or acoustic lens is used to focus a produced shock wave so that as much of its energy as possible converges on the stone. The resulting stresses in the stone cause the stone to break into small pieces which can then be removed easily. 2. Ultrasonic imaging uses the reflection of ultrasonic waves from regions in the interior of the body. It is used for prenatal before the birth examination, detection of anomalous conditions like a tumor, etc., and the study of heart valve action. 3. Ultrasound at a very high power level destroys selective pathological tissues which are helpful in the treatment of arthritis and a certain type of cancer. Underwater applications of acoustics. 1. Sonar, sound navigational ranging, is a technique for locating objects underwater by transmitting a pulse of ultrasonic sound and detecting the reflected pulse. 2. The time delay between transmission of a pulse and the reception of reflected pulse indicates the depth of the object. 3. Motion and position of submerged objects like submarine can be measured with the help of this system. Applications of acoustics in environmental and geological studies. 1. The acoustic principle has important application to environmental problems like noise control. The quiet mass transit vehicle is designed by studying the generation and propagation of sound in the motor's wheels and supporting structures. 2. Reflected and refracted elastic waves passing through the Earth's interior can be measured by applying the principles of acoustics. This is useful in studying the properties of the Earth. 3. Principles of acoustics are applied to detect local anomalies like oil deposits, etc., making it useful for geological studies. Exercises Q2. X page 157. Answer briefly. Define amplitude. Solution. Amplitude A, the largest displacement of a particle of a medium through which the wave is propagating, from its rest position, is called the amplitude of that wave. SI unit is m. Exercises Q2. Sheet page 157. Answer briefly. Define wavelength of a wave. Solution. Wavelength lambda, the distance between two successive particles which are in the same state of vibration, is called the wavelength of the wave. SI unit is m. Solution. Exercises Q2. Sheet page 158. Answer briefly. Define the relation between velocity, wavelength and frequency of the wave. Solution. Exercises Q2. Sheet page 158. Answer briefly. State and explain the principle of superposition of waves. Solution. Principle. As waves don't repulse each other, they overlap in the same region of the space without affecting each other. When two waves overlap, their displacements add vectorially. Explanation. 1. Consider two waves traveling through a medium arriving at a point simultaneously. 2. Let each wave produce its own displacement at that point independent of the others. This displacement can be given as y1 equals displacement due to first wave, y2 equals displacement due to second wave. 3. Then according to the superposition of waves, the resultant displacement at that point is equal to the vector sum of the displacements due to all the waves. Exercises Q2. XIV, page 158. Answer briefly. State the expression for apparent frequency when source of sound and listener are I. Moving towards each other E. Moving away from each other. Solution. Exercises Q2. XV, page 158. Answer briefly. State the expression for apparent frequency when source is stationary and listener is I. Moving towards the source E. Moving away from the source. Solution. Exercises Q2. XVI, page 158. Answer briefly. State the expression for apparent frequency when listener is stationary and source is I. Moving towards the listener E. Moving away from the listener. Solution. Exercises Q2. XVII, page 158. Answer briefly. Explain what is meant by phase of a wave. Solution. 1. The state of the oscillation of a particle is called the phase of the particle. 2. The displacement, direction of velocity, and oscillation number of the particle describe the phase of the particle at a place. Displacement is a function of distance along the wave. 3. Particles r and t, q and u or v and s, have the same displacements but the directions of their velocities are opposite. 4. Particles having same magnitude of displacements and the same direction of velocity are said to be in phase during their respective oscillations. Example. Particles v and p. 5. Separation between two particles which are in phase is wavelength lambda. 6. The two successive particles differ by 1. In their oscillation number, i.e., if particle versus is at its north oscillation, particle p will be at its n+1 th oscillation as the wave is traveling along plus x direction. Exercises Q2. XVII, page 158. Answer briefly. Define progressive wave. Solution. Waves in which a disturbance created at one place travels to distant points and keeps traveling unless stopped by an external force are known as traveling or progressive waves. Exercises Q2. XVII, page 158. Answer briefly. State any four properties of progressive wave. Solution. Properties of progressive waves are amplitude, wavelength, period, double periodicity, frequency and velocity. Progressive waves are classified into two types. A. Transverse progressive waves. B. Longitudinal progressive waves. Characteristics of progressive waves. 1. All the vibrating particles of medium have same amplitude, period, and frequency. 2. State of oscillation, i.e., phase changes from particle to particle. Exercises Q2. XX, page 158. Answer briefly. What is its limitation of velocity of sound? Solution. Limitations of velocity of sound. 1. Experimentally, it is found that the velocity of sound in air at NTP is 332 meters per second. Thus, there is a considerable difference between the value predicted by Newton's formula and the experimental value. 2. The experimental value is 16% greater than the value given by the formula. Newton failed to provide a satisfactory explanation for the difference. Exercises Q3. I, page 158. Solve the following problem. A certain sound wave in air has a speed 340 meters per second and wavelength 1.7 meters for this wave. Calculate A. The frequency. B. The period. Solution. Exercises Q3. E, page 158. Solve the following problem. A tuning fork of frequency 170 Hz produces sound waves of wavelength 2 meters. Calculate the speed of sound. Solution. Given n equals 170 Hz, lambda equals 2 meters. To find velocity of sound b. Formula. B equals n lambda. Calculation. From formula, b equals 170 times 2. Therefore b equals 340 meters per second. The velocity of sound 340 meters per second. Exercises Q3. Page 158. Solve the following problem. An echo sounder in a fishing boat receives an echo from a shoal of fish 0.45 s after it was sent. If the speed of sound in water is 1500 meter per second, how deep is the shoal? Solution. Calculation. For an echo distance traveled by the sound wave equals 2 times distance between echo sounder and shoal d. Exercises Q3. IV page 158. Solve the following problem. A girl stands 170 meters away from a high wall and claps her hands at a steady rate so that each clap coincides with the echo of the one before. A. If she makes 60 claps in 1 minute, what value should be the speed of sound in air? B. Now, she moves to another location and finds that she should now make 45 claps in 1 minute to coincide with successive echoes. Calculate her distance for the new position from the wall. Solution. Exercises Q3. B page 158. Solve the following problem. Sound wave A has period 0.015 s. Sound wave B has a period of 0.025 s. Which sound has greater frequency? Solution. Exercises Q3. B page 158. Solve the following problem. At what temperature will the speed of sound in the air be 1.75 times its speed at STP? Solution. Exercises Q3. B page 158. Solve the following problem. A man standing between two parallel cliffs fires a gun. He hears two echoes, one after 3 seconds, another after 5 seconds. The separation between the two cliffs is 1360 m. What is the speed of sound? Solution. Exercises Q3. B page 158. Solve the following problem. If the velocity of sound in air at a given place on 2 different days of a given week are in the ratio of 1:1.1. Assuming the temperatures on the 2 days to be same, what quantitative conclusion can you draw about the condition on the 2 days? Solution. Exercises Q3. X page 158. Solve the following problem. A police car travels towards a stationary observer at a speed of 15 meters per second. The siren on the car emits a sound of frequency 250 Hz. Calculate the recorded frequency. The speed of sound is 340 meters per second. Solution. Exercises Q3. X page 158. Solve the following problem. The sound emitted from the siren of an ambulance has a frequency of 1500 Hz. The speed of sound is 340 meters per second. Calculate the difference in frequencies heard by a stationary observer at the ambulance initially travels towards and then away from the observer at a speed of 30 meters per second. Solution.
Make it